Dear esteemed audience, today I, Ishan Nagpal, along with my other two team members, Shashwat Singh and Satwik Soumya, are going to present our synopsis for the minor project. The topic for our minor project is implementation of lightweight hash functions for IoT devices. So today, in this modern world, technology and security coexist. Technological advancements have grown more complex and at the same time have made user lives easier and easier. However, with the rise of technology comes a need for security measures. Cryptography is one such measure and that is applied to almost all technological products and services. Cryptography involves the use of mathematical algorithms to protect communication and data from the unauthorized access. It is an essential aspect of securing digital information and is used in almost all aspects of technology, from email encryption to online banking security. However, for smaller devices such as IoT devices and wireless sensors, traditional encryption methods are not applicable due to their limited computational capabilities and resources. The same encryption methods used for mainframes or even the latest portable computers are not suitable for smaller devices like IoT devices as they have limited battery and storage. Thus, lightweight hash algorithms are required for such devices. Lightweight hash functions are designed to be compact and low power and low energy, providing the necessary security for small devices without draining their limited resources. The need for lightweight cryptographic hash functions has been repeatedly expressed by professionals, notably to implement cryptographic protocols in RFID technology. At the time of writing, however, no algorithm exists that provides satisfactory security and performance. The ongoing SHA-3 competition will not help, as it concerns general-purpose designs and focuses on software performance. This is where our project comes in. Our project purpose: a novel design philosophy for lightweight hash functions in order to minimize memory requirements. We focus on developing and implementing the Quark algorithm, which is a lightweight hash function designed specifically for small devices like IoT devices and wireless sensors. The scope of our project is to ensure that the devices that need to be secured are protected using the Quark algorithm. The target beneficiaries of our proposed methodology are those who rely on IoT devices and wireless sensors, as securing these devices has become a crucial task. As the number of IoT devices grows, so does the need for security. Our algorithm, although single security mechanism, is an important step towards securing these devices and protecting our digital information. In conclusion, our project aims to address the need for lightweight hash functions for small devices and believe that the Quark algorithm will be an important step towards securing these devices. The benefits of this project are not limited to just small devices but to all aspects of technology where IoT devices and other sensors can be utilized.
Now let's discuss about the literature review. In the category of lightweight hash functions considered are Spongent 160, Dquark, Photon 160/36, and Keccak are implemented and evaluated based on area, throughput, and power consumption. Cryptographic security is ensured in these hash functions and can be implemented using a small area. They consume less power than the existing hash functions such as SHA-256 and are thus more appropriate for resource-constrained devices. The selection of these hash functions is based on two factors: the security level and the implemented area. For security, the output hash size should not be less than 256-bit. If it is less than that, the security strength will be insufficient. However, the security of the hash function is based on several factors: the output size, the number of rounds, and the word size. The area required for applying the lightweight hash function should be less than 5000 Gs. Those hash functions were selected from this list. The results show that the Quark performs better in terms of throughput, followed by Photon and Spongent. In the evaluation of security in terms of pre-image resistance, second pre-image resistance, and collision resistance, Spongent shows better security, followed by Photon and Quark. Moreover, the consensus protocol that use hash function are expected to perform lightly. However, there was no real evaluation and implementation for these light hash functions as far as energy and power on the same platform. Possible threats to implementation of hashes are pre-image resistance, collision resistance, and second pre-image resistance. Now discussing about the system requirement specification. It is implemented in object-oriented programming language and array are used. A SWOT analysis was done where the strength was that this algorithm is already implemented in different languages, so it is helped us in making the concept clear and making it a Java language. We also provided a possible protection layer by sending it in a ciphertext to be hashed. The only weakness of a project is that the front-end implementation, these are some problems in implementing there are some problems in implementing the functions of object-oriented programming, as we could not implement complex concepts due to shortening of the code. We reduced the code to one round and not to 8 or 16 or 32, which were very time consuming as the code written was in Java, and it is not as fast as C or C++ counterpart for complex purposes. As these lightweight algorithms are already present in the market, so by working on this algorithm, we can further make this with more feature and also work upon a new algorithm with this working principle. Although more and more algorithms can come in the case of lightweight cryptography, the algorithms provide very less of minute difference, whereas in the case of algorithms like SHA-192 or MD5, which being heavy in nature, have an exceptions of being executed as lightweight. As we were using only single security mechanism, these there are some chances that the IoT devices get attacked and the data can be leaked. The project features are: the main function of a project is that the quark instant can be used as a cryptographic hash function as well as a building block of authenticated ciphers. There are four instances in itself. Each has a different layer of security, that is UQuark, at least of 64-bit security, and other possible counterparts, DQuark at least of 80-bit security, and SQuark of 112-bit security. Objectives: lightweight cryptography ensures that the algorithms would be efficient and secure, majorly pre-image resistant, at lower cost. Its main aim is to achieve low cost subjected to good efficiency in hardware as well as software and security of algorithms. Software requirements: the user interface in desktop application. No networking protocols are used, although this algorithm is predicted to be useful for RFID tags. The following are the basic requirements needed for the project: the Windows operating system, a minimum of 4 GB RAM and 512 GBs of storage. Now let's discuss about the software quality attributes. Availability: if the device requires a hash digital signature to maintain integrity, as a specific algorithm can be used for security. Depending upon the input to be hashed or where the hash is stored. The usability: although it maintains the integrity of files of different versions can be used to get different sizes of hash, so more powerful hash values. Testability: we are using Java, so everything is confined to class method, where class or method can be tested for its own functions.
Hello everyone. My name is Satwik Soumya from Batch B for Honors, and I am here to brief you about our project's design and implementations, and finally conclude with our synopsis presentation. Starting with our motivation for the project, the passage on the screen discusses the design of hash functions with the aim of simplicity and security. The use of shift registers instead of S boxes reduces the complexity of circuits in the permutation. Two nonlinear Boolean functions in the four variables were selected to achieve nonlinearity. The rate of execution is reduced to 1 bit at a time to ensure proper mixing of the message bits with state bits. The spawn state is updated 324 times during the absorption phase to achieve the avalanche effect. During the absorption of the intermediate message bits, the spawn state updates 162 times. Absorbing all message bits for 324 times ensures the mixing but results in higher computing power and time consumption. The hash functions generate 160-bit hash. The spawn state is updated once in every permutation. A single bit is squeezed after each permutation in squeezing phase. Now moving on to the next slide. This is the diagram for our project. Now coming on to the system implementations. Our working principle: in the algorithm, the text is broken into components. Although in this code, we return a numerical output, but a binary output is expected, and the input we entered can be encrypted. The text is taken and its character positions are stored. We processed a single round of hash, as repeating of the rounds of the hash would increase processing time, and the heavier the version, the more time it is supposed to take. Our conclusion is working of hashing algorithm. Recommendation: lightweight hashing is useful for RFID technology as it can provide faster methods for transmission. Our milestone: development and understanding of hashing algorithm to implement specific phases of the process to improve understanding. Here are our references, and finally the citations. Thank you everyone for listening.